Okay, so this is the syllabus, Stats 205, Hierarchical Linear Models. Let me go to make this wider. So as you can see, in the syllabus, we have the Zoom link, which you can also find on the CCLE homepage. Since you're already here, I assume you got a link. And the office hour is on Tuesdays from 2:15 to 3:15. Or if it doesn't work for you, you can schedule an appointment with me. And so in short, this is a graduate level course for students in statistics and other related disciplines. We will cover three main topics: advanced linear models, generalized linear models, and linear mixed effect models, which is also called hierarchical linear models. So that's our title. So it's just two terms for the same concept, and including their related statistical concepts, techniques, and algorithms. The course emphasizes on both statistical methodology and applications. Lectures will focus on the motivation, derivation, and understanding of models and methods. Homework will include derivation exercises and practical programming questions. So the requirement for this class includes univariate and multivariate calculus, linear algebra, and undergraduate level linear models. So I will assume that you have already been familiar with the simple and multiple linear models and ordinary least squares. And also on undergrad level mathematical statistics, including maximum likelihood estimation, hypothesis testing, confidence intervals, and asymptotic distribution. So for those things, we actually cover here in our Stats 100B at UCLA. So if this is something you want to make up, you may send me an email and I can refer you to my colleague, Nicholas Crystal. I know he has posted his lectures last quarter, so you may watch his videos to make up those concepts. For example, we'll be directly using the t-test based on the definition of t-distribution. Okay, and scientific programming. So we recommend that you use R because a lot of packages are in R, but if you're familiar with MATLAB or Python, that's also okay. At least you can show your code and submit your code with your homework. Okay, we do not have a mandatory textbook for this course. We only have recommended ones. The first one is what people call the Bible of generalized linear models. So it's a very dense one. It's very thick and dense one, but it's the most comprehensive one today, to my knowledge. And the second one and the third one, they are more applied. So they have R code, they have data sets, a lot of demonstrations. So you may refer to those two books for your further understanding. But in my lecture, I will use my own lecture notes, and they will contain mostly the understanding and the derivation of models. So how do we come up with those models, and how do we do the estimation? Those will be parameter estimation. Those will be the focus of my course. And I will refer you to these books for the applications, and also your homework problems will contain applications. So my goal is that after this course, you will understand better what those R packages and R functions are doing. Instead of just running them and get the output, you understand what's going on inside and what do the output mean. And so we will cover those topics you see here. So we may not finish everyone in this quarter because I realized that the remote teaching, actually our speed is slower for remote teaching because we want to make sure people understand, and this communication is not as effective as the in-person teaching. So we may go slower than before. So for example, I think if time doesn't allow, we may skip the missing data imputation part. Yeah, that's just the plan, but we'll see. But we'll still follow the sequence and see how much we can get done. So regarding the course grades, okay, the homework is half of the grade. And we will have bi-weekly homeworks, and you will submit your homework to CCLE in an electronic copy. So you may use R Markdown. That's strongly encouraged because that's kind of kind of what we call reproducibility, transparency, right? But if you prefer, if you still don't feel comfortable with your LaTeX, you may try to use handwriting for those derivation exercises. If that's the case, you will need to scan your copy, your hard copy, and submit electronic version. And for the second half, so previously for this course, we do a final exam, but I understand that final exam is not a good option for this remote teaching. So we will change this to a survey project. And since we have a rather big class, so I would encourage that you try to find a partner and form a group with no more than 2 students. If you prefer to work by yourself, that's also okay. So we will have groups with either 1 student or 2 students. So every group would choose a survey topic related to our class materials. So for example, the topic may be applications of the models we cover in this class to a specific field like biology, like social science. And you may also survey new methodology development of the models we talk about, like extensions of the model we talk about. Or you may survey computational issues regarding to the models, like how do people use faster estimation techniques, right? So that's one topic. And if you're unsure of your topic of choice, you may come to my office hours to discuss. And please start early. That's my suggestion. But I understand you may also want to see like we cover enough material so you get a better sense about the survey topic. So I would say probably it would be a good idea to start working on your survey project in week 5, week 6, around that time. And so because we don't want you to write too much, we will ask for a limit on length. So the length of the paper will be limited to no more than 6 pages, but this excludes figures, tables, or references. So you can still put those outside the page limit. And font size, single space. And in the last week, we will ask you to do a 10-minute oral presentation in class. So this time is calculated given that you form groups of 2 students. But if we have more groups, we may reduce this oral presentation time. So we'll see. So I think we will ask for your group assignment probably around week 6, week 7, around that time. So please find your partners early. And your papers will be submitted by the end of the final week. So that's just the grades. And so for the policy, for this time, I would like to ask everyone, if possible, to turn on your video during the Zoom class sessions. I think this is a way for us to have better communication. I can see your facial expression to see whether you're confused or you understand. And I think that can also give you a more disciplined way in listening to the lecture. Probably that will be helpful. But if you do have some special concerns, for example, you don't feel comfortable with showing your room or something like that, or if you have to attend this class remotely, I understand that. So that's okay. You can just let me know. But I would want to encourage everyone to turn on the video during the class. Okay, so I think that's it. So do you have any questions about the syllabus? And also email. Please make sure that you receive the CCLE emails I sent before. If not, probably there's some registration issue or the email address might have some issue. So just make sure. I sent an email about the Zoom link. Yeah, so I think you should have received that. Okay, so if you don't have questions, I'll stop sharing the syllabus. And since this is our first lecture, and we have 25 students here today, probably we can do a quick introduction by each one of you. So you can talk about like, what's your major? Are you a master's student, PhD student? And have you ever used linear model in your research? I think that's something I would like to learn. And so probably we can start just, with the order I see on my screen. Max, maybe you can go first.
Hi, my name's Max. I'm a PhD student in political science. Yes, I've used linear models in my research before. Sorry, what were the other pieces of information that were relevant?
I think that's it.
Okay.
Yeah, I said whether you're a master's student or PhD student, but you said you're a PhD student.
Okay.
Oh, sorry. My last question. Yeah, actually, I have one more thing. So, what motivated you to take this class?
Oh, well, I wanted to learn more about generalized linear or hierarchical and linear models in general, some of the assumptions that underlie linear models, and also I just needed to take more stats classes in general.
I see. And also, I think for those of you who have ever encountered or used hierarchical linear models or generalized linear model, maybe you can say some of your confusions you had before. So I think that can also help me for my lectures. So if you see something's really confusing to you, you can bring it up during the introduction. Okay, thank you, Max. And next, Adam. Adam wrote.
Yep. Hey, everybody. I'm Adam. I'm a master's student in the stats department. I'm hoping to get into the PhD program. We'll see. And I'm doing research on like sensitivity and frameworks for selection bias in linear models. And so I figured taking more classes on linear models will help me have a stronger foundation for that.
Okay, great. Thank you. And Ali, I see there's Ali's iPad.
Yes, hello everyone, my name is Ali. I'm a PhD student at computer science. My research lies in the intersection of computer science and biology, and my research involves linear models. And I think this course would be useful and related to my research area. Yeah.
Okay, great, welcome. And next, thank you. Yeah, next, Ashley.
Hi, I'm Ashley. I am a second-year master's student in the stats department. Like I think I also went to UCLA for undergrad, so linear models is one of the techniques that's like really heavily emphasized in the program. So I've used a lot of that in just my own personal data analysis. But separately, I've also TA'd for a couple of undergraduate courses where they use linear regression. So particularly the aspect that you mentioned about kind of understanding more of the theory of the underlying packages that we use in R that we teach to the undergrads is one of the primary goals and reasons why I'm taking the course. And I've also taken a couple of other courses with you and really enjoyed your teaching. So
thank you. And Derek Holiday.
Hi, I'm Derek. I'm a fourth-year PhD student in political science. My research involves differences in representation in national and local politics, which involves data from sort of multiple different levels of aggregation. So I think hierarchical linear models would be a good way to solve some of the problems associated with that.
Okay, welcome. And Evan Becker.
Hi, everyone. I'm Evan. I'm a first-year PhD student in computer science. I have used linear models a bit in my research, but I guess I'm looking to get more of a foundational understanding of those.
Okay, yeah. Next, G Lee, if that's the correct pronunciation.
Yeah. Hi, my name is G. I'm a PhD student in social welfare. I am planning on using one of the linear models for my dissertation. So I wanted to learn more about it. So that's why I'm taking this class. And I've used binomial regression before, but I'm still confused on how to choose Poisson versus binomial. So that's something that I'm hoping to learn more about it from this class too.
Welcome. And next one is Mr. Gregory Leslie.
Hey, what's going on, everyone? My name is Greg. I'm a PhD student in political science. I study mixed race politics and kind of how social context informs people's politics. We do a ton of modeling, but when we learned regression, it was from a terrible professor. So I want to learn more about what's going on under the hood with some of the techniques we use.
Okay, hopefully we can feel you that this course is not terrible. And next one, Howry iPhone.
Hello everyone, my name is Howry Sun. I'm a PhD student in Civil and Environmental Engineering department. And my major is hydrology and water resources. So I'm focused. My research focused on the data assimilation. I think this class is useful for my research and about the data analysis. So I take this class. Thank you.
Thank you. Okay, next, Ian.
Hi, I'm Ian. I'm a second year master's student in the statistics department, and I'm taking this class, well, primarily because of taking a couple classes with you and I like them. And also I have figure if I'm getting a stats degree, I should take a more focused class on linear models. I kind of have a blind spot to them.
I see. Thank you. Next one, Jia.
Yeah, hi, my name is Jai. I'm a second year master's student from the stats program. My research is in learning theory, and I haven't used much linear model in my research yet, but I'm excited to learn more and explore more. Like Ian and Ashley mentioned, I was also in your 201 class last year, and I really enjoyed the style that you teach. So yeah, I'm excited for this class.
Okay, welcome. Okay, next one, let me see, is Ji-Yoon or Ji-Hoon?
Yeah. Hi, my name is Ji-Hyun Oh. I'm a second year doctoral student in social welfare. I have used the linear model, and through this class, I want to gain a better understanding hierarchical linear model. Thank you. Nice to meet you.
Nice to meet you too. Next one, Johnson Chen.
Oh, hi, everybody. I'm a second year PhD student in the CS department, and my research kind of works around biology and healthcare related to like computer science part. So I've briefly used linear mixed model before to handle kind of like there's some correlation between the samples you collect, but I never really understand how it works from the math part. So I was trying to figure it out and discuss.
Okay, great. Okay, I think maybe your research is related to genetics, I will assume.
Yeah. Genetic.
Linear mixed model used a lot. Yeah. Okay, Kang Cheng next.
Hi, I'm Kang Cheng, and I'm a second year bioinformatics PhD student. And like as Jessica just mentioned, so my research focus is on statistical genetics, and we use like linear mixed model all the time. So I want to have a systematic understanding of the topic in this class and hope to learn more.
Okay, welcome. Next one, Li Feng. Li Feng fan.
Hello, I'm here. So I'm a fifth year PhD student in the statistics department, and in my research, I just found the hierarchical statistical modeling is like pretty useful, and I use a lot in my research. So I'm very interested in this class and want to learn more. Yeah, that's it.
Okay, welcome. Yeah, we still have a fifth year PhD student here. So I will assume that usually when people are in their fifth year, they no longer take classes.
Yeah, just need to take classes to finish the credit requirement.
I see. Yeah. Okay, welcome. And next one is Mikhail.
Hi, yeah, I'm Michal, and I'm a second year PhD student in the bioinformatics program, and I work in the area of GWAS and TWAS. So linear model is like is the main tool. So this is why I'm taking this class.
Okay, welcome. And next one is Michelle.
Hi, my name is Michelle. I'm a PhD student in community health sciences. I am interested in taking this class. My dissertation is looking at maternal health care and also looking at effects within facilities, so kind of women nested within facilities. So have a basic understanding of HLM, but wanted to strengthen my foundational understanding.
Okay, welcome. Next one is Nadav, if that's the correct pronunciation, N-A-D-A-V.
Yeah, hey, it's Nadav. I am a PhD student I've worked with the hierarchical models in my research, and I want to get deeper understanding on the different degeneracies and how to solve them.
Which major are you in?
Computer science.
Computer science. Okay. Welcome. Next one, Nathan.
Hello, I'm a PhD student in sociology, and I've used some hierarchical linear modeling with education data, and I'd like to better what's going on and how to choose model selection and assess model fit.
Okay. Next one, Seed or S-A-E-D. Seed.
Yeah, it's Saeed. Hi, everyone. I am Saeed. I'm a third year PhD student in operations management. Basically, hierarchical linear models are not directly related to my research, but it's generally a useful type of research that we do. So that's why I'm interested to learn more about the details of these models. Yeah.
Okay. Welcome. Next one, Yijia.
Hi everyone, I'm Yijia Zhao. I'm a first year PhD student in the Department of Statistics. I come here to learn more about generalized linear model, and I've heard that you are very good at teaching.
Thank you. And so your first year, did you come here yet? Are you at UCLA?
Yeah, I'm here because I received my master's degree in USA, so I didn't come back so I can stay here. Yeah.
I see. Okay. Well, nice to see you remotely. Next one, Zach.
Hi, I'm Zach. I'm a second year student, PhD student in the operations management program. Linear models are not directly related to my research, but in TAing for an introduction statistics class, I found that I could use more support in explaining model selection in particular in linear models.
I see. Okay, welcome. Nice to see you again, Zach. Yeah, I saw that several of you were in my last quarter's class, so it's nice to see you here again. I think I cover everyone. If I miss anyone, please let me know. Yeah, because the order kept changing, but I think we have covered everyone. So from the introduction, you can see that this class is quite diverse, right? We have students from statistics for sure, and also I see many of you come from social sciences, including political science, social welfare, sociology. We also have students coming from CS and bioinformatics, and also civil engineering. So I think you can use this opportunity to find your partner, probably outside of your field, so that you can have some synergy during the collaboration. So yeah, but I understand the remote collaboration may not be so easy. So this will depend on how you reach out to people to find a partner, especially if you don't know someone already. So if you cannot, you can work by yourself. So still you can do the project just by having yourself as the group. Okay, so that's the introduction. And if there are no more questions, I think we'll start our lecture. So for those of you who have listened to my last quarter's class, I think we have been quite successful with using my projector and pen and paper. So I think I'll keep doing that because previously I have been teaching this class using the blackboard. So now I think the paper and pencil will be like the closest replacement. And for the lecture notes, the typed up ones, you can check them out on CCLE. These were subscribed by previous year students. If you spot any typos, mistakes, you can send me emails and we'll make the correction. So we'll try to refine the notes as the year goes on. So that's the plan. And also, I want to say that in the first lecture notes, a student did a very good job by defining the notations in LaTeX. You can check them out. Although I cannot really write notations as perfect as in the typing, but I'll try to make you understand, okay, this is a scalar, this is a vector, this is a random scalar, this is a random vector. So in LaTeX, these can be easily distinguished, but not so much in handwriting. So if you have any questions, you can ask me anytime. So that's another thing the reason I want everybody to turn your video if possible. That is, if you ask a question during the class, if your video is on, I can see your face. So that is like more like communication. Otherwise, I can only hear the voice without seeing anyone. That's kind of weird to me. Okay, So I will start sharing the screen. Give me 1 second. Let me try to find that. Okay. Okay, I'm going to share this app, as you can see. So I'll make this full screen so you can see better. All right. So today, since this is our first lecture, we will just start from simple linear model. So if you have ever heard of it. So simple linear model means that we have only one predictor. And this is the case where we can make a scatter plot with x-axis as the predictor value, y-axis as the response value. But before going to that, let's just introduce the notations we use in this class. So we use this constant notations. We will use the constant n to stand for number of observations. Okay, so you may understand the observations as your data points. That's what people use in some contexts. And I know in computer science or machine learning, some people refer to those as instances. So these actually refer to the same thing in our class, and we will stick with observations. That's the number of data points you draw or you sample. And P is another constant. Here we refer to it as the number, well, I should say 1 plus the number of predictors. So predictor also has other terms in the statistical literature. Some people call it covariance. Okay, in machine learning, some people call it features. And sometimes people call this explanatory variable. So these terms coexist in the literature, but I just want to make sure that we understand they are the same thing here. And here the +1 means that we include intercept into P. So that's why we have the +1. So N and P are most commonly used throughout this class. And you know, in machine learning, sometimes people use P to denote people use D instead of P. They use D as the dimension, but here we use P. Okay. And also in this class, if we do not specify, we would assume all the vectors are column vectors. Okay, because vectors are column vectors, so then if we write an inner product or dot product of two vectors, we will write A transpose B. So if, let's say, A and B are both p-dimensional, okay, because here we assume vectors are column vectors. And that's the notation throughout this class. And so with those notations, let's start with the simple linear model. By simple, we mean that there's only one predictor. So in undergraduate context, right? So what we assume is that when there's a simple linear model, we will write out every observation. So in this case, what we will do is that we will say here the predictor, we call it X. It is a scalar. Let me see this. Okay, and the response we call Y. It is also a scalar. And what we do here is that we assume we have n observations of the predictor and the response. And so the simple linear model is written as, let me just write it here. So I go from 1 to n. So in this writing, when I use those notations, basically everything is scalar. There's no vector here. And we call this beta 0 the intercept. Intercept is always a scalar. And we call this beta 1 the slope. And this is what we call the error term. So in this class, I want to differentiate or distinguish the error term from the residual. So please note that these two do not mean the same thing in this class. So error term are part of our model. It is a random variable, while residual is what we obtain after fitting a model. So residual is the result of model fitting, while error term doesn't involve any model fitting. It's just an assumption. It's in your model setting. Okay, so we'll come back to that later, but I'm just bringing it up here. And so in this writing, you see, I'm basically writing y as the uppercase, x as the uppercase, and epsilon is a Greek letter. So when we're writing uppercase, we refer to random variables. When we write in lowercase, we refer to constants. So in this writing, we are basically assuming xi and yi are both random. Okay, so when xi, yi, epsilon I, so if we assume them to be a random triplet, in this case, what do we call it? Since we refer to xi as random, we call this random design. So what does design mean? So before teaching this course, I actually checked the literature, and I noticed that in the term design matrix, which we'll see later, design matrix here, if we just define it for the simple linear model, it will actually be intercept appear for n times x1 to xn. That will be our design matrix. So here it's n by 2. You can see p equals 2. So why do we call this a design matrix? The reason is from a field in subfield in statistics called experimental design. So that's when people perform experiments. They will actually choose to collect observations by specifying the predictor values or the covariance values. So they will assume, okay, this is how I designed the experiments, and then I collect the data. I would observe how the yi would occur. So one thing you can imagine for experimental design is drug design. So if you want to test the drug effect, you can specify x1 to xn as n dosages. And then you use the drug on your patient. And then you observe the drug effects as your yi. So in that case, you can see the design matrix is set up by yourself. And because of that, we actually, in statistics, most of the cases, we talk about fixed design. So when we say we talk about fixed design, we basically assume x1 to xn, as you can see, now I'm writing in lowercase, are fixed. So the design matrix is just this. I'm using lowercase. And the simple linear model becomes yi equals beta 0 plus beta 1 lowercase xi plus epsilon I from 1 to n. So in this case, when we talk about fixed design, the error term is the only source of randomness. And as a result, yi is a random variable. So you see, Here in the simple linear model with the fixed design, the randomness becomes much easier. We don't consider xi to be random, but just epsilon I to be random. And this is the classical setting in statistics. So you may wonder, why do we choose fixed design instead of random design in statistics? So for this discussion, I posted a discussion paper to CCLE under week 1. You can check them out. So in that paper, they thoroughly discussed the historical origin and the justification of fixed design, and also discussed how linear model can be used as an approximation of nonlinear model. But just to put it in short, so there are several advantages of assuming fixed design. First of all, it makes our probability distribution easier. So in statistics, a lot of time we use likelihood. And if you are under fixed design, writing the likelihood of parameters beta 0 and beta 1 and the variance term of epsilon I is much easier. So often we assume, I didn't put this, we assume that epsilon i's are IID, identically and independently distributed with mean 0 and common variance sigma squared. So in the linear model setting, this is called the homoscedasticity assumption. So in statistics, people often assume that. So you see that now we reduce the model to just 3 parameters, beta 0, beta 1, sigma. And we can write down the likelihood very easily. So that's the convenience reason. Another reason why fixed design is reasonable if you assume the true model is linear model is what we call in statistics, is called an ancillary principle. And this ancillary principle is related to data generation. So if we believe that a data generation is, we first sample our predictor values in our design. Given the predictor values, we generate our yi. If that's what we assume, then we can see the joint density. So I'm just going to call that as x, y. The joint density of x and y can be written as the conditional density of y given x times the marginal density of x. And if we say that the linear model has those parameters, maybe I can call them theta, okay? I'll define beta 0, beta 1, sigma as my theta. Then the theta is only involved in this conditional distribution of y given x. And probably x itself has its own parameter, I'll call it psi. But you see that x marginal distribution is not related to this theta. So in statistics, we say that x is ancillary to theta. Ancillary for theta. In other words, the marginal distribution of x has nothing to do with the estimation of theta. And how do we see that more clearly? So let's say that here, this distribution, joint distribution involves theta and psi for sure. Let's say we consider 2 possible values of theta, theta 1 and theta 2. If I compare the density ratio given theta 1 over the density given theta 2, you see, in statistics, this is what we do when we do likelihood ratio, right? So this is the likelihood for theta 1, this is the likelihood for theta 2. And on the right-hand side, since psi stays the same, it would just be equal to this conditional density given theta 1 divided by the conditional density given theta 2. So you see, related to theta 1, regarding the distinction of theta 1 and theta 2, this marginal distribution of x doesn't play a role. So because of this, people assume, okay, it's reasonable to do the conditional inference of theta just based on conditioning on X. By conditioning on X, we don't lose information about the inference of data. So that's what we call the ancillary principle. And that's why statisticians use this to justify the use of fixed design. But talking about that discussion paper, so one interesting point is that this whole discussion is under the assumption that the linear model is the correct model. If it's not a correct model, then this principle has some issue. It's not applicable because the theta itself would be related to the marginal distribution. So we cannot write it this way. So to give you an intuitive illustration, you can think of it like this. So that's why I start with the simple linear model, because we can draw the graph. So given this is one predictor and this is y. So you see that if the true relationship, I'm going to draw a line. If this is what we have expectation of y given x, okay? So if the linear model is correct, then that should be beta 0 plus beta 1x. This is the true model. And you see that we want to estimate this model. So regardless of the distribution of x being here, let's say if I draw a distribution here, then most of the data points will be drawn here, or the distribution being here, I can still estimate the line, right? Because the slope remains the same and the intercept remains the same. So no matter where my distribution is, whether my distribution is this one or this one, my estimation will be roughly the same, right? So this is why we say, okay, the marginal distribution of x do not affect the estimation of the line. But I'm just saying in a very rough sense. So if I want to be more clear, we will see that the variance of x does affect. For example, if my data points are just concentrated on one point, if the distribution is like this, okay, if x is a point mass, then there's no way for me to estimate the line because there can be infinite number of points, right? Infinite number of lines that can explain the data. So that's a special case. But here I'm just assuming, okay, x has a reasonable variance. There's no singularity issue. So in terms of linear algebra, just to skip a little bit, in terms of linear algebra, this point mass will give me what? You see, in the design matrix, I will basically have, let's see, this is C. I will have C, and that is a singularity issue because my two columns are essentially one column, and we'll have an issue in our least square, but we'll talk about this later. So I'm just bringing this up for now. So, but if the true relationship is nonlinear, you can clearly see that the marginal distribution matters. Okay, if this is the true relationship, and we're using linear model. So what we're doing is that, so let's say this is the margin distribution. So our data points will be here, right? And linear model is like an approximation for this nonlinear relationship. So we may estimate the line as this, if our x are distributed like this. But if our x is distributed like that in this region, then the approximation will be different. And you can see that our estimation, the linear model estimation will change as the marginal distribution of x changes. So that's why in that discussion paper, it says, okay, the fixed design makes sense only when you assume the linear model is the correct model. But still, I want to say that statistical inference, the whole topic of statistical inference is trying to talk about parameters, right? Parameters in a model. And by talking about the inference of parameters, you are assuming the model is a reasonable model to be considered as the truth. That's why you do the inference. But on the other hand, we should bear in mind that all models are wrong, right? All models are wrong, some are useful. So that's the thing we should keep in mind. So in other words, we should always be aware that our inference is conditional on our model. So this is the concept I want to instill in our first class. So inference. It's about the estimation of model parameters. And This is by assuming the model is reasonable. And this whole concept of inference is still the core of statistics. And it is in slight contrast to what we call prediction. Prediction has become the, I would say, the focus of machine learning most of the time. So by prediction, what we mean is that we are interested in predicting the response. So y1 hat to yn hat, that's our focus. And we're interested in how close they are to y1 to yn. So this is what we call supervised learning. And this is where machine learning has been very, very successful. So if our prediction is our focus, then we care less about the parameters of our model, whether we can interpret them, but we care more about the prediction results. So that's why you see that when the task is prediction heavy, for example, computer vision, people actually sacrifice the model interpretation a lot. They use neural networks. They will not talk about the neural network parameter, whether they're 0 or not, whether they can do a statistical test or not. At least for now, that's still not the primary concern. They concern about this prediction, and they could afford to use a rather complicated model. But on the other hand, linear model, right? We know for sure it cannot be 100% correct. How can the reality be linear? But still, it's still so popular, especially in social science and genetics. And you may wonder why. The reason is that it has very good inference. We can do parameter inference in a very reasonable and rigorous way. So then you can talk about what's the range of the parameter, right? Like the confidence interval concept. And then you can use that result to make stories out of your model. So in social science, people use linear model not for prediction's sake a lot, but they want to use it for interpretation a lot. And that's related to model inference. So I would say our class here will largely focus on inference. Although we'll still talk about prediction a little, but that's still not a focus. And you can imagine if prediction is your primary focus, nowadays you have a lot more complicated tools to use rather than linear models. Okay, so that's the very high level introduction. And also one more thing I want to say is that, so for those simple models as linear models, they still have advantages when your number of observations is too small. Or let's revisit here. One more thing I should say about this N is in statistics, people call this sample size. I forgot to say that. When your sample size is too small, in that case, and the noise is too big. So in that case, you cannot really afford to fit a too complicated model. So linear model will be your best bet. All right, so let's revisit the simple linear model. So now we have talked about the fixed design and the random design. And from now on, this whole class will focus on the fixed design. So we have written the fixed design in the scalar form, right? So yi equals beta 0 plus beta 1 xi plus epsilon I. I go from 1 to n. Now let's put it in the vector form. So, or matrix form. Matrix form of simple linear model. So we stack y1 to yn. That's the response vector. And we put the design matrix 1, x1 to xn. Please note that I'm using the lowercase for fixed design now. Times, we have this column to be multiplied by beta 0, second column to be multiplied by beta 1. So using the matrix multiplication, I have beta 0, beta 1. Okay, and then finally, I have my error term stacked, epsilon 1 to epsilon n. So if we look at the dimension, so this is an n by 1, this is a n by 2, 2 by 1, n by 1. And we're going to use this vector form from now on. So we're going to denote this as y, denote this as x, this as beta, this as epsilon. So now they're all vectors or matrices. This is a matrix. So although here you cannot easily distinguish them from the scalar notation, but I just want to make sure that you understand that from now on, we're going to use this vector form for our linear model. And this form can allow us to easily generalize this model to more than one predictor, because you can see as a generalization, I would have, so the P becomes greater than 2. I can just have this as M by P, and this is P by 1. And P is not necessarily 2. I can include more predictors as additional columns. Okay, and given this notation, given this vector form, we can also dissect it into 2 layers. And we're going to use those 2 layers throughout this course. It's not just a linear model. We're going to talk about those 2 layers for generalized linear model and also linear mixed effect models. So there are 2 layers of structure. So the first one we called systematic structure. It's not regarding any randomness. It's about a fixed relationship, we assume. And by the way, so throughout this course, I think one core thing I want you to keep in mind or remind yourself is, where is the randomness? So when we write down a model, this is the first thing you want to look at. Where is the randomness? What is the random variable? So in this model, the randomness comes from epsilon. This is the random vector. And this is okay, maybe I'll use a different color. So this is random. This is fixed. This is random. Okay, so then the systematic structure is only about the fixed part. So in other words, it's about how the expectation of the response is related to the design matrix. That's what we call the systematic structure. And there is, I now spot there's a typo in the notes. I'm going to correct that. So in the systematic structure, we have this expectation of yi. And for this one, we give it a notation, mu I. We're going to use mu I to refer to the expectation of yi, and that's a scalar. And this one, we say it's equal to xi transpose beta. And so here, one thing I need to make a correction about the notation is this. So when we have the design matrix, okay, given the design matrix, we write it as x1 transpose to xn transpose. So in the simple linear model, each row will contain one, the intercept, and xi. So that's why there's like an abuse of notation, because I cannot use boldface here. So this is about the row vector, not just a scalar. So that's why we can see that when we do this matrix multiplication, each yi is equal to xi, the row transpose, the xi transpose times beta plus the epsilon I. So that's the systematic structure here. And the second structure is what we call the random structure. This is related to where the randomness comes from for the model. And this is the key part, right? It's about how we can specify the model likelihood. So the random structure here is actually because of this epsilon I, right? So given that epsilon I is normal distribution, IID actually, 0 sigma square. That's the random part. And if we translate this into the randomness of yi, we will be able to see that this gives us yi, each yi is independently distributed with mean as the expectation, xi transpose beta, variance sigma square. So why do I change IID to independent? The reason is that here the yi's, different yi's have different means because their means are determined by xi. Since xi's are different, so the means are different. So I cannot say they are identically distributed. I can only say they are independently distributed. And they still have the common variance. So you see the two layers of structure. One is about the mean of yi, mean of yi, and the other is about the distribution of yi. And we're going to see that this whole structure or this dissection will be applicable to any generalized linear models. By generalization, over there, we change the distribution of yi. So it may not be normal anymore. It could be binomial. It could be Poisson. It could be negative binomial. So those are the generalization. But still, for all the GLM or generalized linear models, we can always dissect them into a systematic structure about the mean of yi and the random structure about the distribution of yi. Okay, so as I said, the key for linear model is parameter inference. So now let's come back to that topic. Let's go to that topic, parameter inference. So here we have two parameters. One is the coefficient vector beta, p-dimensional. The other is the variance term, sigma squared. That's a scalar, right? So we have those two things. And our primary parameter of interest is beta. Why is that? The reason is if we write it out, we can see that the beta includes the intercept and the slope of p minus 1 predictors. And each slope is actually what we call the effect size of that predictor. It reflects how much does that predictor value change affect the changes in the response value. So the larger the magnitude of each beta j, the larger the effect that predictor j has. So that's why we want to often do this to really understand the effect of a predictor on the response. So how do we do the inference then? So we rely on likelihood-based inference. So then we need to define the likelihood. So here, the likelihood is about two things, beta and sigma squared. So for now, we just assume sigma squared to be known for our convenience. We start from there. So then the only parameter we need to do inference about is beta. And we know that the likelihood of beta is defined as the joint distribution of our observation. So it's the joint distribution of y1 to yn even beta. So this is one thing I want to clarify as probably a reminder of the mathematical statistics course. So even though we write equal here, but joint density in nature is different from likelihood because they take different arguments. In a likelihood function, the argument is the parameter, while in the density function, the argument is the random variable you observe. So in other words, for the joint density function here, its argument, it has n arguments, y1 to yn. While in the likelihood function, the argument is beta. So if beta is p-dimensional, it takes p arguments. So that's why even though we write equal, we use the density to define the likelihood, but essentially they are two different functions because their arguments are different. Okay, so one more thing is that by saying the density, what we assume is that the beta is fixed, but the n values y1 to yn may change. And while we write the likelihood, we assume the data is fixed. Y1 to yn are fixed, but the beta value can change. So that's why I say they are talking about different arguments. So here, because of the independence assumption, right, y1 to yn are independent, we can factorize them. So we can factorize them as the marginal density of yi given beta. And now we can use that yi are normally distributed with xi transpose beta sigma squared. We can use this. And that can easily give us the likelihood function. Just use the normal density. Okay, this is the normal density and we multiply them together. So in mathematical statistics, because of the factorization, we have to deal with the product. But it's much easier if we do a log transformation, so we can change the product to summation and we can get rid of the exponential term. Right, so then the log likelihood, we use lowercase l. That will be simply negative n over 2 log 2 pi sigma squared minus 2 sigma squared summation yi minus xi transpose beta squared. Okay, so now for this term, what can we say about it? So this square term, if you're familiar with the vector inner product, this is actually equal to, if we use the vector form, y minus x beta transpose times y minus x beta. If we do that, it's just the sum of the squares. And we know that by the MLE principle, maximum likelihood estimation, we want to maximize this log likelihood. And that will be equivalent if we assume this is known, right? So beta is only involved in this term. That will be equivalent to minimize this. So we would say arg max L beta. We want to find the beta that maximizes log likelihood and we take the maximizer. That's what we call arg max. It's actually equal to the arg min of y minus x beta transpose y minus x beta. We can also write this as the L2 norm squared, and the L2 norm is about y minus x beta. So we can write it that way. So maybe just one more line. We can also write it this way. That's the L2 norm. Okay, so then how do we do the minimization? That's what we call ordinary least square. Ordinary least squares. And this technique actually came from Gauss in, I would say, maybe 400 years ago, around that time. So, and that concept, ordinary least square, was actually way before the likelihood was introduced or invented in statistics literature. So this is a very naive or I would say intuitive, I shouldn't say naive, intuitive thinking, right? So you want to take the sum of the squared differences. Yi is the thing you want to predict, and xi beta is your predictive model. You take their differences, take the difference and take the square to remove the sign, and then you take the sum. You want to minimize that. But just by coincidence, this is equivalent to the MLE. I think that's something very interesting to know. So we use the Mle approach and we arrive at the ordinary least square. And what's remain is to solve for beta. And now you can see that the vector form will make the least square solution a lot more easier than we were in the scalar form. Okay, so we try to, and this is a convex function, convex in beta. So we know there's a global minimizer. So we just want to take the gradient or derivative against beta. So then we do d beta of this y minus x beta transpose times y minus x beta. Now I can do expansion. So expansion will give me y transpose y minus 2y transpose x beta plus beta transpose x beta. Okay, and a principle in matrix calculus is that if you have this form and you do the derivative, you will keep 2y transpose x, and for the other term, you will keep 2 times beta transpose times x transpose times x, or 2 times x transpose x times beta. So either one is the same, because that will give you a scalar. Oh, sorry, that will give you a vector, p-dimensional vector. So we'll come back to this later. I remember in our later class, we'll give you a much more deeper introduction to the vector calculus. But here in this class, you can just assume, okay, this is a scalar, right? Now we are taking its gradient against beta. Beta is a p-dimensional vector. So this gradient, by our definition, will be a p-dimensional vector. So just keep that in mind. So then the result will be a p-dimensional vector. And here I'm just telling you that it's negative 2 times y transpose x. You can verify that this is p-dimensional, plus x 2 times x transpose x beta. You can also verify that this is p-dimensional. Okay, and we want to set this to 0 to solve for beta. And by setting this to 0, we can actually see that we obtain this equation. X transpose x beta equals x transpose y. Oops, I think I made a mistake here. It should be like negative 2x transpose y. Yeah, that will be p-dimensional for that. So this is the equation by solving this, and we give this a name. And we're going to see this name again when we talk about generalized linear model. This is what we call the normal equation. By terming this or defining this as a normal equation, you can see its importance. So it's actually giving a very important result about the relationship between beta and y. And by solving this, we actually obtain our estimate. Okay, so solving this, we obtain beta hat equals x transpose x inverse x transpose y. So by doing that, we can do that only when this x transpose x is invertible. This is a P by P matrix by our definition. And it is also symmetric. It is invertible if and only if it is full rank, right? Its rank is equal to P. Otherwise, it doesn't have an inverse. So in most cases, we are fine with this. But if it's not invertible, often in some textbook, people call this people write this as the pseudo inverse. That's just the inverse that satisfies this equation, but it may not be the unique solution. Okay, so here now we are just talking about the invertible case. And we have this as the OLS estimate. So X transpose X is invertible. This is equivalent to that X has full column rank. Okay, and this is equivalent to that all the columns in X are linearly independent of each other. So that's a concept in linear algebra. So columns of X are linearly independent. So we cannot write any column as a linear combination of other columns, in other words. So in our observed design matrix, usually, right, the real data we obtain, the x's are observed. We do not usually encounter this issue. But if we are back in the experimental design case, since the design matrix is what we arbitrarily design, we should avoid the linear independence here. Okay, so given this most important result, the OLS estimate, that's in statistics called point estimate. In other words, we have found an estimate for the unknown parameter, but we are not satisfied yet. We want to talk about its uncertainty, not just getting its value. So when we talk about parameter inference, we are usually concerned about two aspects. One is called a bias of an estimate. One is the variance. So bias is defined as the expectation of the estimator minus the true parameter value. So here, given the definition, we can calculate expectation easily. And you can see here the fixed design will greatly help us. Because in the fixed design, the design matrix is fixed. We can get any fixed terms, fixed factors outside of expectation. So this becomes X transpose X inverse X transpose expected Y. Y is the only random variable minus beta. And we know that this is equal to X beta from our systematic structure. Then you see we have an easy cancellation of X transpose X, and that gives me 0. So which suggests that the OLS estimate is unbiased. That's the first property. The second property about the variance, we can still use that fixed design to greatly help us. So for the variance, if we have the variance beta hat, and see here, because beta has p-dimensional, so this so-called variance is in fact a p by p covariance matrix. It's not a scalar variance. Okay, even though we're still using the same variance notation. And now let's use that formula again. X transpose X inverse X transpose Y. Again, here, the only random vector is Y. But we need to get this out, okay? So here is one thing I want to say about the covariance matrix. We know that in the variance, if it's a scalar, then the scalar multiplier will be squared once it gets out of the variance. And here we have something similar. So we are going to, so this is a property, I'm going to write it here. So the variance of, let's say, A times Y, okay? Say what is n by 1, A is P by M. So A will represent this product here. So if we do get it out, A out of the variance calculation, we will actually get A times the variance of y times A transpose. So this is the property we're going to use here. And you can still verify the dimension to see why it's reasonable. This is P by N. This is an N by N covariance. This is an N by P. So if you multiply them together, you get a P by P covariance matrix for A times Y. Okay, so coming up here, we will have X transpose X inverse X transpose Y times, variance Y times the transpose of the left-hand side, and that will give me X times X transpose X inverse, because this inverse is symmetric. And what is the variance of Y? Now that will help me a lot. We know every yi are independently normal with the same variance sigma square. So we know this is equal to sigma square times identity. This is an n-dimensional identity matrix. So we can basically move sigma square to the front. And moving this to the front, we can see that X transpose X are together, and we can cancel out one copy, and we will get sigma square times X transpose X inverse. This is the second most important result about linear modeling. We can say this. So it's about the variance of the least square estimate. Okay, so we will stop here for today. The class time is up, and we'll continue from here next time. So I just want to make sure that you understand, although we started from simple linear model, but currently our discussion using the matrix form is applicable to multiple linear model. So the design matrix can contain more than one predictor. So all those formula will be useful, will still hold. Okay, so that's all for today, and we will continue from here next time. So see you on Thursday.